Hello again. This is Math 2-115 coming to you from the College of DuPage. The title of this lecture is Midterm Solutions, Spring 22. As always, please be an attentive learner while watching this video. First problem involved a hardware logic design that I gave you, and you were to determine the output values given the inputs. This is a truth table problem, and your answer should be 1, 1, 0, 1, 0, 1, 0, 1. Next problem. In a version of the computer language BASIC, the name of a variable is a string of 1 or 2 alphanumeric characters, where uppercase and lowercase letters are not distinguished. An alphanumeric character is either one of the 26 English letters or one of the 10 digits. Moreover, a variable name must begin with a letter and must be different from 5 strings of 2 characters that are reserved for programming use. How many different variable names are there in this version of BASIC? Well, there are 2 possibilities. You can have 1 character or 2 character. 1 character, since it must begin with an alphabet character, there are only 26 possibilities. If you have a 2 character, you can have 1 letter, which begins the variable, but then you can either have a letter or a number for the second. So that means we have 26 times now 36, because 26 plus the 10 digits gives you 36. So I multiply those together and I get 936. But I must subtract off the 5 variables that are reserved for programming use. So that is 931. I add these 2 numbers and I get 957, the answer. Next question. What is the least number of area codes needed to guarantee that the 25 million phones in a state can be assigned distinct 10-digit phone numbers? And we assume that each telephone number is of the form NXX, that's the area code, NXX, that's the exchange number, and then XXXX, where the first 3 digits form the area code. N represents a digit from 2 to 9 inclusive, and X represents any digit. So for any individual area code, we can have 8 choices for this first N, and then times 10 times 10 times 10 times 10 times 10 times 10. That means for each area code, we can have 8 million numbers. But that means if I have 1 area code, I have 8 million people served, 2, 16 million served, 3, 24 million served. So to serve 25 million, I need at least 4 area codes. The next problem involves McCarthys 91 function. So consider capital M of n is equal to n minus 10 if n is bigger than 100. And it's m of n plus 11 if n is less than or equal to 100 for all positive n. I asked you to compute what is the value of z, which is m of 101 plus m of 76. Okay, so m of 101 is easy. I plug it into the number, I get the top, I subtract 1, and so when I subtract 10 from 101, I get 91, and that's the answer to the first part. But then I have to add it to m of 76. Now m of 76 is equal to m of, I add 11 to 76, getting 87. This is a more involved calculation. So m of 87 is m of 98, which is m of 109, which is m of 99, which is m of 110, which is m of 100, which is m of 111, which is m of 101, which is m of 91, which is m of 102, which is m of now 92, and that's m of 103, which is m of 93. Now the pattern continues, increasing. So you just this is ratcheting up. So you see I'm going from 91 to 92 to 93 all the way up to 99, 100, and 101. So eventually this is equal to m of 101, and that is going to be 91 again. Now we know that m of 76 then was m of 91, but we found out here that m of 91 ends up being 91. So we get 91 plus 91 is 182 is the final answer to the problem. This 91 function was introduced in papers by a series of authors, including John McCarthy, in 1970, and these were representing early developments towards the application of formal methods of program verification. The 91 function was chosen for being nested recursive and was popularized in books about the theory of computation in the mid-70s. As the field of formal methods advanced, this example appeared repeatedly in research literature. In particular, is viewed as a challenge problem for automated program verification. And in fact, you can prove that the McCarthy M function actually is equal to m of n is equal to n minus 10 if n is greater than 100, and it's always 91 if you have any n less than or equal to 100. And this is proven by induction, and it's strong induction downward, which is a little bit different than what we've talked about. So for n greater than 100, what happens is it happens just directly from the definition. For n less than or equal to 100, we can talk about strong induction downward from 100 can be used. And in particular from 90 to 100 inclusive, this argument will work, and you will find that m of n is equal to m of n plus 1. So that means that these will ratchet themselves up as we found, and eventually they will hit m of 101, and that will be 91 between these numbers. Now this is our base case, and this can be used as the base case, but for the induction step we're going to let m be less than or equal to 89, and we assume that m of I is equal to 91 for all I that are bigger than n and less than or equal to 100, which were the ones that we're talking about here. Then we find that m of n is m of n plus 11 by definition, but that is equal to m of 91 by hypothesis, which is equal to 91 by the base case. So this proves that m of 91 is equal to 91 for all n less than or equal to 100, including actually negative values. The next problem asks us to consider the following data tables. So we had supplier, parts, and projects, and we also had inventory. We had part number, project, quantity, and the color code. Turns out we don't use the color code, but we are having a query, so we want to select the supplier and project from the parts need database and from the parts inventory database where the quantity is less than or equal to 10. And so you want to give an answer that is going to tell us who are the suppliers and what are the projects. Okay, so we have to be less than or equal to 10, so we identify these from the parts inventory, and then we take those parts numbers and we find those in the parts needs, and we link them with the suppliers and the project numbers. And so the answer to the problem is these are ordered pairs: 23, 1, 23, 3, 31, 3, and 32, 4. The next problem. A group of 15 candidates for 7 identical positions consists of 6 women and 9 men. If the candidates are randomly selected to fill the positions in such a way that there are more women hired than men, how many different possible sets of hired individuals are possible? And you need to count here. Now, there were 7 identical positions, and that means to have more women than men. Either you have 4 women, 5 women, or 6 women, which are disjoint situations. And so, if you're not hiring a woman, you're hiring a man. So here, what will happen is you have 15 candidates. So to figure out how to hire the women, you would take 6 combinations taken, 4 at a time, to pick how many different ways you can hire the women. And then you have to multiply that by the remaining positions, which would be 3, are selected from the 9 men. So this is 9, choose 3. If there are 5 women, it would be 6, choose 5, times 9, choose 2. And if there were 6 women, it would be 6, choose 6, and 9, choose 1. And you multiply those things together, and you add them, and you get 1485. The next problem dealt with strings. Let A sub I be the set of all non-empty bit streams. And so they have length of at least 1 and not exceeding I. And I is 1, 2, and 3, as you can see here. So what is the union of the A sub i's? Well, here's a distinct list of the union of the A sub i's. You also could have described this as A3 because they're nested. A3 contains all A1 and A2. And the intersection, which would be this set of bit streams, which would be A1. And so either you can have the explicit answer or call this one A1 and this one A3. Problem number 8. An exam has 12 problems. How many ways can positive integer values be assigned to the problems if the total points is 100 and each problem is worth at least 5 points? Well, we're going to say that we got 12 problems at least worth 5 points, so that means 60 problem points are accounted for. So we're talking about distributing 40 amongst the 12. Now this is what we referred to as a stars and bars problem. So 40 points are to be distributed among 12 problems remaining. So in a jargon that we used when we proved the theorem, we have 40 points is N, and K is 12 problems. So it is a combination. It is N plus K minus 1, choose K minus 1. And so when you choose that, what you will get is, 40 plus K minus 1 is 51, and then K minus 1 is 11. So it's 51, choose 11. It is this number. This is something over 47 billion. The next problem, you were to prove or disprove that the ceiling function of x plus y is equal to the ceiling function of x plus the ceiling function of y for all real numbers x and y. Now, this is not true, and you give me a counterexample. You could say that x, and actually I'm going to say that x equal y equal 0.1. Then over here I'd have 0.1, 0.1. Both of those would be 1. So that's 1 plus 1. That would be 2, where over here you would get 1, and 1 does not equal to 2. Here was a flow chart, and I ask you to input A to be 91 and B to be 63 and compute what happens. And the answer is 7. And this is a formula using the Euclidean algorithm that you would recognize by now because we've had some lectures since then. So this is the greatest common divisor between 91 and 63 is 7. Here, the last problem, you were to demonstrate whether the function introduced in an earlier problem, this was the 91 function, is a one-to-one function. Well, it's not a one-to-one function, so you prove that it's not because m of 101 is the same thing as m of 76, but 101 does not equal 76. And so that would be a good example to demonstrate that this is not a one-to-one function. Now my rubric is each of these 11 problems is going to be scored out of 10, and then I will compute a percentage with a perfect being. If you got 10 on every problem, that would be 110. And then I'll take that ratio and I'll round the percentages up for your score on the exam. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself because self-care is important, and of each other because we're all in this together. We can and should make a difference. God bless you all.